Regions in the complex plane. Regions in the complex plane. Before we can rigorously develop a good foundation for the concept of function and limits, we need some set theoretic definition that will presumably come in handy later. Definition: an epsilon neighborhood point of Z0, often denoted as NS, Z2, is the set of all points Z lying inside but not on a circle of the radius epsilon, center at Z0. That means n epsilon Z0 is equal to Z belongs to C, that is complex number, such that Z minus Z0 modulo is less than epsilon. It is understood that when we speak of the neighborhood, we are speaking of the epsilon neighborhood. Also note that the value of epsilon is unspecified. It could be 0.1, 1000, that is or 42, whatever we need for the current circumstance. Topologists are fond of calling this structure that is a open ball. This is a open ball. That is Z minus Z0 modulus is the radii. Here this is the epsilon. This is the center is a Z0. So this is the x-axis, this is y-axis. Epsilon neighborhood definition: a deleted neighborhood, also called puncture disk of point Z0, is an epsilon neighborhood of Z0 that does not contain Z0. In set theoretic notation, we can write the deleted neighborhood of Z0 as n epsilon Z0 or Z0 in curly bracket. Definition: an interior point is a point Z0 of a set S such that there exists some neighborhoods of Z0 that is entirely contained in S, or there exists epsilon greater than 0 such that n epsilon Z0 is a subset of S. Definition: an exterior point E is a point Z0 such that there exists some neighborhood of Z0 containing no point in S, or there exists epsilon is greater than 0 such that n epsilon Z0 is not a subset of S. Now definition: the boundary point is a point Z0, a set S that is neither an interior point of S or an exterior point of S. Equivalently, a boundary point is a point Z0 such that every neighborhood of Z0 contains at least one point in S and at least one point not in S. That means, or for all epsilon is greater than 0, there exists P1, P2 belongs to n epsilon Z0 such that P1 is belongs to S and P2 is not belongs to S. Definition: the boundaries of a set S is the set of boundary point of S. Definition: an open set is a set that contains none of its boundary points. A set is a open if and only each of its point is an interior point. Definition: a closed set is a set that contains all of its boundary points. Note that not being open does not imply being closed. Example, if a set contains single boundary point, it is not open, but it is not closed either. Also note that a set can be both open and closed. For example, complex number has no boundary point, so it contains all of them. Yet each of its point is an interior point, so it is both open and closed. A tongue-in-cheek name for such set is clopen. Definition: the closure of the set is the closed set consisting of all points in S together with the boundary of S, denoted by CLS. The closure can be thought of as an operation to a set. Now, definition. A connected set is an open set such that any pair of points Z1, Z0, Z2 belongs to S can be joined by a polygonal line that lies entire in S. Definition. A polygonal line is a finite number of segments joined end to end, endpoint joined, like this is a polygonal. So it is a connected set also. Definition. A domain is a non-empty, open, connected set. Note that any neighborhood is a domain. Definition. A region is a domain together with none, some, or all of its boundary points. Definition. A set is bounded if every point in S lies inside some circle Z magnitude is equal to R with some finite radius R. Otherwise, S is unbounded. Definition. An accumulation point of a set is a point Z0 such that every deleted neighborhood of Z0 contains at least one point of S. Note that closed set contain all of their accumulation points. Example, is the set S curly bracket Z belongs to complex such that real of Z is greater than 1 and imaginary of Z is greater than 2. Okay, that is open or closed or neither. How can a set be neither open or closed? We can say that is a imaginary region. This is a 2I, this is a 1. This is a real axis. A set that is neither open nor closed. Neither open nor closed. So, we ask ourselves, does S contain any points in boundary point? Is it open? No. So, S contains at least one of its boundary point. So, it is therefore not open. Does it contains all of the boundary point? Is it closed? No. S is missing a part of boundary. Okay, namely that imaginary. Imaginary of Z is equal to 2 boundary. So, therefore, S is not closed. We can say that that the definition of open and closed are not opposite. A set can be neither open nor closed. For example, now consider the set a complex. First we ask if a complex has a boundary point. It does not. Does C contains all of its O or boundary points? Yes. Also complex does not contain O boundary point because they do not exist. Complex C is therefore both open and closed. What about that is equal to 5 or 0? It is certainly does not contain any of its boundary points, namely because it is contains absolutely nothing. However, as there are no boundary point to contain, it contains all of them. So the empty set is both empty and closed. Now, what about S? Curly bracket Z belongs to complex. Real of Z is greater than equal to 1 and imaginary of Z is greater than equal to 2, Z is not equal to 0, illustrated below. That means here region is mentioned. That region, this is imaginary region, this is real region. The region is here mentioned. Now, what if we take T is equal to S union 0, or rather include 0 in the above set? That means this set, imaginary set, this is 2i, this is 1, that the real axis is there. So, it is a closed set. How it is a closed set? Now, T does not contain all of its boundary points. So, T is closed. We also ask ourselves again, if T is open, but because it contains at least one of its boundary points, so T is not open. Because, one example, finally consider set S is equal to Z belongs to complex, real Z is greater than 1, imaginary Z is greater than 2. Here is open. Why? This is imaginary, this is real. So, this is an open set. This set is open because does not contain any of its boundary point, means it is greater than is there, no equal to symbol is there. Now, consider example, set S is equal to Z, it belongs to complex, imaginary Z is greater than 1, down below. That means this figure comes. So, this figure comes. This is real axis, this is imaginary axis. So, this is a simple domain. We ask ourselves a series of questions about S. Is it open? Yes, it contains none of the boundary points. Is it bounded? No, the set goes on the forever positive y direction and along real axis. Is it connected? Yes, every pair of point in S can be joined by the polygonal line. Is it domain? Yes, it's non-empty, open and connected. Example, now consider the region bounded by the inequality. Z minus 4 magnitude is greater than Z modulus. Graphing certainly making interpreting region in the complex plane easier. So, work on the simplifying the above inequality into something we can work with. First, we use the definition of the modulus of a complex number. X minus 4 whole square plus y square is root over is greater than x square plus y square or root over. Since the modulus is by the definition positive, we can square both sides without committing a mathematical sign. So, z minus 4 whole square plus y square is greater than equal to x square plus y square. X minus 4 whole square plus y square is greater than equal to x square plus y square. X square minus 8x plus 16 is greater than equal to x square car. So, 16 is greater than equal to 8a. So, 2 is greater than equal to x. In other words, we are dealing with the set S where Z is belongs to complex and real Z is less than equal to 2. That is in response. This is the real axis Z, that is 2, okay, that is position. So, which is a simple region. That means this set is closed, not open, not a domain, not a bounded region. Now take another question. What about S? Z is belongs to S, Z is not equal to 0, 0 less than argument of Z is less than equal to 4. That is in imaginary axis. You can draw that is pi by 4 theta is given. This is real axis. So that it is a simple region. This is not on open. It is also not closed. Z is not belongs to S. Not domain, not bounded, but it is simple connected region. Now example. Now consider the region of the complex plane defined by the inequality real of Z magnitude less than 1 less than Z modulus. Using our brains grasp, we might be able to convince ourselves that is inequality is true unless Z is belongs to real. However, to make sure we perform the algebra. Now, real of Z is magnitude is less than Z magnitude, X magnitude less than X square plus Y square root over X square modulus square is less than X square plus Y square, A square square cotiola, 0 is less than Y square, 0 is less than plus or minus Y. That means real and imaginary axis is there. That is so simple. This is a here. Similarly, consider the set Zn is equal to I by n, where n is belongs to natural number. In that time, I is here mentioned is I by 2, this is I by 3 in that way. Real is an accumulation point is there. This point is accumulation point. Now, this note that O is not contained in the set, so we can get as close as well like to O, but we can never get there. That means that O is a boundary point on Zn. Also note that every point is not an interior point. As a neighborhood point, any point is not in entire contained in Zn. So let us consider the deleted neighborhood O. No matter what absolutely peak, we can always find an element of Zn that within the deleted neighborhood. This means that every deleted neighborhood of O contains at least one point of Zn. So O is an accumulation point Zn. We can also see that O is the only accumulation point of Zn, because no matter what point we pick, there will always be some distance between the point we pick and its neighbors. That is not in Zn. Also note that O is Zn's only boundary point. So CL Zn is equal to Zn comma 0, or close to Zn. So now consider another example also. I minus 1 I1, that is minus 1 1 minus I. So set with no accumulation point. This set has no accumulation point. Similarly, this also comes. This is a accumulation point.